Yeah, I'm Dr. Tom Allen, one of the co-hosts of the CCPO-ICAR seminar series, and glad to have everybody here today, especially Dr. David Munoz, who I met over the summer, and we got to striking up a correspondence on interest in coastal storms and flooding, sea level rise, and all the hybrid hazards that we're facing these days. He is a professor at Virginia Tech. Recently, he runs a Coral Lab. You see a really cool logo there. He's got a bachelor's from University of Cuenca in Ecuador, master's from Wageningen, and a PhD from Alabama, if I'm not right. So a lot of collaborations in coastal hydrology, data science approaches, and even digital twins. So I'm very excited to have you here, David. And I'll hand it off to let you take it away with the presentation.
Okay, thank you very much, Tom, for the introduction. Let me just hide the video so I can see. Okay, good afternoon, everyone. My name is Dave Munoz. I am assistant professor at Virginia Tech. And my talk is about integrated modeling perspective of compound flooding by using hybrid approaches. And what is that? Basically, a combination of state-of-the-art modeling techniques that includes, for example, statistical methods, process-based modeling, or hydrodynamic models, and machine learning techniques. I want to acknowledge my PhD students because part of the research that I'm going to present is basically their current research. Okay. So I want to start this presentation by showing you a figure with the most expensive disasters or hazards in the United States. This is called the 2024 $1 billion weather and climate disasters. And as you can see, the US is vulnerable to multiple hazards, from droughts to floods, hurricanes, tornadoes, wildfires, and so on and so forth. Unfortunately, this figure is not updated yet. We can see just Hurricane Beryl right here, but we are missing information about Hurricane Helene, for example. But this is just, a snapshot in time this year. If we go back in time and we consider multiple hazards from 1980, for example, to 2018, what we can see is that in the past 2 decades, the frequency and intensity of tropical cyclones, so the pink spirals, have increasing over time, and also the costs associated with them. So we can see Hurricane Katrina, Hurricane Harvey, Hurricane Maria among the most expensive disasters in the United States. As I mentioned before, we need information about Hurricane Helene, for example, and I expect that that hurricane will be among the most expensive disasters as well. So providing actionable compound flood information is crucial, and this is needed because the information that we can provide as a modelers, statistical or process-based modelers, can guide the decisions that emergency managers adopt, support all those preparedness as well. One common issue is that sometimes we think of tropical cyclones affecting just coastal areas, and that's sometimes not the case, and Hurricane Helene is the proof of that. And you can see, for example, that torrential rainfall and the storm associated with Hurricane Helene affected the NOAA National Center of Environmental Information, the headquarters in Asheville. So the chart, the figure that I showed at the beginning with the $1 billion disaster hasn't been updated, and partially because Asheville is without power energy, and cannot update that information. So providing that information, as I said, is crucial. And if we go through like newspapers, we see common issues with flood hazard characterization, for example. For example, this one, the New York Times says that the problem with the hurricane category rating, and the thing is that we rely on metrics, for example, the Saffir-Simpson scale, that relies on wind speed to establish the different categories of hurricanes. And it doesn't account of terrestrial and coastal flood drivers, for example, that can also play a role in establishing the hazards or delineating the flood hazard zones in different areas. Another headline of the Washington Post is like how healing became a worst case scenario. And the problem is that we fail in really or properly characterize those compound flood hazards. So if we ignore the dependencies, the statistical dependence between different drivers, it's obvious that we will not be able to really capture the flood zones, the maximum water level in different areas. So with that brief background, I want to introduce a formal definition of compound flooding, which is basically the combination of multiple drivers or hazards. So for example, precipitation and storm surge. So those drivers or hazards are not necessarily extreme, because you could have extreme storm surge and just the average river flow, for example, and that combination can lead to compound flooding. So the combination of those drivers produce larger flood impacts than those from isolated drivers. And the schematic that you are seeing in the screen is basically the mechanism behind compound flooding. So you have a modulator, the low pressure system that controls different drivers, for example, heavy rainfall and storm surge, that in combination or multiple succession lead to flooding and also to flood damages and costs. Now, if we account for the effects or impacts of climate change or anthropogenic activities as well, we expect larger flood damages, especially in coastal areas that are vulnerable to flooding. I like this animation of NASA Emerge. This is a precipitation product from NASA. It's showing rainfall in millimeters per hour, and it shows the track of Hurricane Helene. So the problem with compound flooding is that we think that the flood drivers occur at the same time, and that's not usually the case. So for example, you see that in Asheville, in North Carolina, and even in Georgia, even before Hurricane Helene made landfall, there was a torrential rainfall that saturated the soil, and as a result of that, we saw that many flash flood events in Asheville, for example. So accounting for those dependencies of rainfall and storm surge and wind as well, help us really characterize compound flood hazards. So compound flood modeling requires a solid understanding of processes, of physical processes, and that includes obviously the water cycle, the different pools or the places where water is stored, and the different fluxes, so the ways that water moves between different pools. So understanding those processes, as well as the relevant flow drivers that lead to compound flooding. So for example, storm surge, rainfall, river flow, surface runoff, really help us to characterize those compound flood hazards. When we account for also the effects of climate change, if we talk about sea level rise in coastal areas, anthropogenic activities like groundwater extraction that leads to land subsidence, for example, all those processes need to be understood to really account for dependencies and also be able to generate more accurate flood hazard maps. Compound flood modeling requires also a solid understanding of statistics. And that includes, as I mentioned before, the dependence between different flow drivers and processes. So in this study, for example, we combined a process-based model with a statistical analysis to provide high tide flow thresholds for the continuous United States. One of the challenges that we encounter is that, for example, let's take a look at the Big Bend in Florida. So you see those two dots with the black circle. Those are actually gauge stations, tide gauge stations that record information water level. So if we want to establish high tide flow thresholds, there is nothing in between. So understanding the statistics, dependencies between the processes, using process-based models, we were able to fill those gaps and provide now high tide flow thresholds with a spatial interval of 10 kilometers for entire coastal of the United States. The problem with the statistical dependencies is that most of the analysis, the statistical analysis that are used for estimating, for example, return periods, ignore any dependencies or take one driver at a time. So let's say if I want to estimate the hurricane, the return period of Hurricane Helene, for example, what I will do is to, for example, rely on the tide gauge station, infer the probability distribution function, and then from that, say, okay, from my observations, let's say I have a water level of 2.5 meters, and that corresponds with 100 or 200-year return period, more or less. So that kind of give me the intuition of what is the return period associated with a hurricane event. Now, the problem is that when I have multiple drivers, so let's say that I have river flow affecting an estuary system. So it's not only water level, but river flow that lead to compound flood hazards. So accounting for the dependencies is challenging and require a solid understanding of statistical processes. So I will, there are multiple challenges in compound flood modeling, and I want to focus just on three that I think that are the most important. And I have some examples that I can show you how I address those challenges. So the first one is compound flood modeling is challenging due to statistical dependencies, and we see that a linear superposition of flood drivers often lead to large errors if we want to project water levels or even delineate flood hazard zones. So this schematic shows the ocean and river channel, for example, or land at the right. And we have mean sea level, high tide, low tides. So what FEMA, the Federal Emergency Management Agency, suggests to characterize flood hazards is to rely on two different flood or process-based model simulations. So the first one, the first scenario consists of, okay, using a non-extreme storm source. So for example, values above mean high water, and also as a inland or upstream boundary condition, a river flow associated with a 100-year return period event. That's the first simulation. The second one is the opposite. Let's take a 100-year return period event, water level associated with that, and then a non-extreme river flow, for example, the average annual discharge. So FEMA says, okay, take the composite of those two water level profiles, so the blue line, and that's the maximum water level that you should expect for any given return period. And as you see, it accounts for one driver at a time in a way in terms of return periods. And based on that, you have the different flood hazard zones that you see that are available for the US. So don't get me wrong, this is a practical approach because it requires just two model simulations and it can be super fast. The problem is that in reality, if you don't account for statistical dependencies, you may experience those issues like, for example, Hurricane Harvey, about 50% of the houses that were impacted or were flooded were outside those flood hazard zones that were established by FEMA. So that points out to the importance of accounting for those dependencies. Another challenge, the second one, is the nonlinear interactions that can emerge between the different components of water level and also processes, hydrometeorological, coastal, oceanic, and anthropogenic activities. So this set of equations is basically the different components of extreme coastal water level, mean sea level, storm tide, and the storm tide can be divided into high tide or harmonic tides and non-tidal residual. So the different interactions lead to nonlinear interactions. And based on that, we can also associate the effects of sea level rise. So in this study, what we did is to basically analyze the change of the potential maximal surge tide. So the interaction between surge and tide with respect to sea level rise. So you see the figure at the global scale, how a change of sea level rise in millimeters lead to change in the interactions between surge and tide. But this is not the only nonlinear interactions that we have. So sometimes we have, or in reality, we have interactions between climate indices and water level, teleconnections, for example. So in this study from Wall and Chambers, they analyze how the different climate indices affect the extreme water level estimation. So what they did is basically account for climate indices such as the El Nino, the North Pacific Index, the Pacific Decadal Oscillation, and so on and so forth, and see how those different climate indices are correlated with water level. And they show that when we estimate return water levels, there are some changes through time. And that's basically, in a nutshell, non-stationarity, how non-stationarity also affects the estimation of the return water levels. If we assume that everything remains the same, then obviously we will underestimate the compound flood hazards that we see today. And the last challenge that I want to discuss today and present some applications of hybrid approaches consists of cascading uncertainty in compound flood modeling. The schematic shows the different sources of uncertainty in any environmental system models, and that includes model parameters, uncertainty for forcing data or boundary conditions, uncertainty from the initial state of the system, model outputs, and observations. So if I want to translate this information into the context of compound flood modeling, I can categorize all the four main types of uncertainties. The first one, the initial condition, which, for example, the static digital elevation model that we use in process-based models, soil moisture that can be an input depending on the software that you use, and water level. Forcing data, all the boundary conditions, hydrological, meteorological, oceanic. So for example, river flow, precipitation, wind, atmospheric pressure, coastal water level, and those boundary conditions that we usually account for when developing the process-based models. And model parameters are basically roughness values that we use to calibrate the hydrodynamic models. Model structure, that basically refers to the model configuration of the process-based models, the numerical scheme that we use to solve the momentum and mass balance equations, and that depends on the software. So that's the fourth source of uncertainty. So based on those three challenges, now I will show you how different hybrid modeling strategies help address or overcome those challenges. So the first one is hybrid process-based and statistical models. So how to combine process-based models and statistics to characterize flood hazards. And I want to start this by showing you some evidence. So the correlation between many flood drivers, terrestrial and coastal in the US, is statistically significant. That means that the p-value is less than 0.05. So this nice figure from Munoz et al. Shows the different correlations between drivers. So for example, storm surge and river flow, storm surge and precipitation, storm surge and waves, and so on and so forth. And you see the different stations, tide gauge stations in the East Coast, Gulf Coast, and West Coast. The asterisks represent the drivers that exhibit correlation that is not statistically significant, whereas the other ones, those correlations are not that high in some pairs of drivers, but still statistically significant. So for example, Sewell's points in Virginia, we see that storm surge and precipitation are correlated with, that correlation is statistically significant, storm surge and waves and precipitation. If we focus in Cedar Cay in Florida, where close to the area where Hurricane Helene made landfall, we see that most of the flow drivers, terrestrial and coastal drivers, are highly correlated, with the exception of river flow and waves. So that indicates that we need to account for the statistical dependency if we want to develop or create a statistical or flood hazard scenarios. So in those cases, let's say that I have two flood drivers, river flow and water level, and I want to estimate a return period associated with a 50-year, then a univariate approach would tell me that, for example, river flow, the magnitudes should be, let's say, 45,000 cubic meters per second, right? And then in terms of water level, about 0.65 or so. And then you will use the FEM approach to establish what is the water level, or to determine what is the water level, and also delineate the flood hazard zones. But in reality, if you account for the dependencies of a 50-year return period event, so you sample the data and follow the contour line of the point of and find the point of maximum probability density. So this combination of flow drivers are basically characterizing the 50-year return period event, in contrast to the other ones. And you may think that, okay, if I do this, I will underestimate flood hazards. And I will show you that that's not the case. So accounting for the statistical dependence can even lead to higher water levels than those of univariate approaches when you account one driver at a time. So this is an example of hybrid process-based and statistical modeling for coastal flood hazard assessment. So here what we did is basically develop a hydrodynamic model for Savannah River Delta in Georgia, at the border of Georgia and South Carolina. We calibrated the model in terms of water level and velocity. The good thing about this study is that we found some velocity observations from the USGS, and we were able to calibrate the model for velocity as well, something that is not really usual in hydrodynamic models. And then we follow the same approach. We account for the dependencies between, in this case, the non-tidal residual and river flow, and establish a return period of 50 years. And then we played with the DEM to account for vertical errors within wetland areas. So it is well known that LiDAR-derived digital elevation models cannot really capture the true vertical elevation, especially within wetland areas, and that depends on the vegetation height. So by accounting for those errors, we have two types of DEMs, with and without elevation correction. And we played with the different forcing conditions, univariate analysis, the MH, which is basically maximum water height, and the average river flow. And MQ is the maximum or the return period of river discharge and a non-extreme storm surge. The ANT that you are seeing there is basically the copula approach, the statistical analysis that accounts for the two drivers, and then you have the DM with and without the elevation correction. And we conducted an analysis in terms of flood depth and flood velocity, once again, because we were able to calibrate the model for velocity. And we used the Taylor diagrams to see how the different combination, or how the compound effect of flood drivers and wind elevation affects coastal flood hazards. So the way to interpret this Taylor diagram is, okay, focusing on the black dot, which is the model that accounts for everything, the most, or the benchmark model that accounts for the elevation correction, for the statistical dependence of the different drivers. So the closer the dots that you see here, the more accurate the models are with respect to the baseline. And we see, for example, that if we rely on univariate approaches, so let's say the pink and green dots that you see here that correspond to the MQ, the maximum river discharge, with and without elevation correction, then we are underestimating, or we are having large errors when estimating, in this case, flood depth. The same analysis can be done in terms of flood velocity. So another thing that we did in this study is to compare, to analyze or to really identify the return period of Hurricane Matthew in this case. So one way to do that is, as I mentioned, we feed a univariate distribution, and then we find what is the actual observation during Hurricane Matthew in this case, and then based on that figure, estimate the return period. So another way to characterize the return period of a hurricane event is to using or leveraging the process-based model. So in this case, I'm showing you some results of velocity of Hurricane Matthew in the Savannah River Delta. So this is the actual hurricane event. And what I did is to calculate the residual. So the maximum velocity associated with this combination of flow drivers and with and without wetland elevation correction. And then what is the residual with respect to the actual hurricane event. So those two here are basically the marginals, so maximum river flow, maximum water level. And this one, the ANT, which is accounting for the statistical dependence, led to the smallest residuals. So meaning that this scenario is closer to the actual hurricane event, as you can see here. So the red colors indicate an overestimation of velocity, the blue color an underestimation of velocity, of maximum velocity. Moving forward, another application of process-based and statistical models help us account for climate change. So for example, how sea level rise will affect tidal range or water levels, how anthropogenic activities, for example, dredging protocols, will affect vessel navigability and wetland inundation. So in this study, we developed, again, a process-based model in Delft3D for Mobile Bay. You see here the black line showing the dredging channel that ensures transportation from the Gulf of Mexico to the port in Mobile Bay. And we have different profiles. And the whole idea was to analyze the dredging protocols that the U.S. Army Corps of Engineers have to or consider to analyze the effects of dredging on wetland dynamics, because the concern was, okay, if I dredge this channel by 1 meter or so, what will be the effect on the wetlands that are located downstream and upstream? So what we did is to follow that approach, and in addition to that, account for the dependencies between the different flow drivers, so in this case, river flow and water level. And for example, this chart shows different profiles. The black line is the baseline scenario with and without the dredging protocols. And the different colors, the combinations of, for example, low river flow, low water level, high river flow, high water level, and CF is the compound flow scenario. Once again, the dashed lines represent the dredged condition. And we see that in terms of tidal range, you may expect that the high scenario lead to the highest tidal range or so. But accounting for the dependence of drivers, we see that the compound flooding is actually the one that is showing you the most extreme conditions. And in terms of vessel navigability, what we did is to also create those nice navigation charts that informs, okay, what are the conditions, what are the combinations of water level and river flow that ensure a safe clearance of those vessels, and the areas that the vessel can experience damage, for example. And what we also notice is that there are some areas, the cyan, the purple, and the blue color, that correspond to minor, moderate flooding and major flooding. And we saw that, for example, in terms of wetland ecosystems, by considering those combination of flow drivers, the flood stages also shift towards the right. So you see that, for example, the HH scenario is in the major flood stage, but if you consider the dependence between the flow drivers, we ended up with a higher or more risky scenario in terms of water level. So that's another application of process-based and statistical models. Another application consists of integrating process-based models and machine learning. And that's the state of the art right now in terms of characterizing or predicting compound flooding and also extreme water levels. So in this study, what we did is to leverage all available information in terms of tide gauge, time series data, and also remote sensing observations. So the model that you see here, hydrodynamic modeling, is basically the one that I developed for Savannah River Delta. And what I did is to fuse the information from process-based models and remote sensing imagery at the same time, and a space, obviously, that coincide in time and space, and use a convolutional neural network to learn from different patterns and spatiotemporal associations between that information, and then conduct land cover and flood mapping at a larger scale. So this was at a local scale, and the model that was trained and validated in Savannah was applied over the southeast coast of the United States. To validate the model, we consider high water marks from the USGS, that's the ground-truth flood information that we have, and also the hindcast flood maps from the Coastal Emergency Risk Assessment, so the one that is providing forecasts for the hurricanes in the Gulf of Mexico and the Atlantic coast. So the results are, in general, good. We were able to map not only delineate land cover classes, but also flood classes. So one thing that is important to mention here is that machine learning needs physical constraints to be accurate. For example, if we think about wetlands that by definition are periodically inundated, so high tide, low tide, but when you have a hurricane event, those wetlands are also inundated. So there should be a threshold that informs us, okay, those wetlands, even though they are periodically inundated, if the water level is above that threshold, that means that those wetlands are inundated. So that's what we did in this framework. We introduced a threshold value in the training process, so the model can really distinguish between permanent of open water and also flood water, even between wetland areas. And then we assessed or we evaluated the model performance in terms of capturing the high water marks. So we have, for example, the red color that is the flood maps from the framework that we developed, the convolutional neural network in data fusion, and CIRA. So the areas that those two agree. So we saw that around 80% of those flood areas match, so are similar. Now we see the cyan color that represents areas that were not captured by CERA, and the blue areas that are flooded areas that were captured by this process-based model, the operational search model, and were not captured by the CNN framework. The different dots, the yellow dots, represent basically the high water marks from the USGS. So when analyzing those different high water marks, we found out that in some areas, the framework that we developed is way better than the operational search model. So you see, for example, in Georgia, around 52% or 53% of the high water marks were captured by the CNN model, and just 5.26 of those high water marks were captured by the operational search model, the process-based model, at CIRC, in other words. In other areas, we saw that CIRA works very well, so 44%, and then our framework is not really capturing some high water marks. But overall, the whole message here is that fusing satellite imagery, combining those process-based models, introducing physical constraints, help account for those different processes and cover or reach to the points where the CERA model didn't capture any flooding. So in this case, the number of high water marks that were captured by the CNN framework is twice the ones that were captured by the process-based model CERA. So 38 or 39 versus 19%. Another application, and this is one of the studies of my first PhD student, and it's basically applying transfer learning in terms of water level evolution, extreme water level evolution for tropical cyclones and extratropical cyclone events. And what is the motivation behind that is that we know that if we develop, for example, a process-based model for Beaufort in North Carolina, for example, this is the model domain. One of the limitations with process-based models is that we cannot transfer that model to other areas because those models depend on site-specific conditions and boundary conditions that might not be the same in other areas. So the advantage of machine learning model is that those models learn from data patterns between input features rather than specific magnitudes. So if you have a combination of different drivers and site-specific conditions, there is a pattern behind that the machine learning model is trained, learn from that, and is able to infer a target variable. So for example, extreme water levels. So in this study, Samuel, my first PhD student, developed a bidirectional long short-term memory network, and he added an attention mechanism layer to improve the performance of the model. So here's just a capture schematic of the training validation process and the hyperparameters that we use to calibrate the model. So as you can imagine, if you have a machine learning model, let's say at Beaufort, North Carolina, the green dot, the hyperparameters that are used to calibrate that model may not be the same as in other stations. So to overcome that challenge in transfer learning, what we did is to develop multiple models and then select the ones that meet a given criteria in order to be used in other stations. So in other words, what we did is add all those dots with colors. Those are the training stations. So we have a LSTM model, bidirectional LSTM model for that. And black dots are basically stations in between that we want to transfer our model and estimate extreme water level. Obviously, because those black dots are actual tide gauge stations, we have information to validate or to see or to evaluate the performance of transfer learning and the models that we use. The challenge with that is that for LSTM, by definition, the models learn from long-term sequential patterns, which means that if you split the data, let's say in training set and testing set, in some stations, for example, in Atlantic City, New Jersey, we saw that the most extreme values were not part of the training data set. And that's one of the well-known challenges that we have when characterizing long-term sequences. So if you use another machine learning model, let's say random forest, if you want, and you can just focus on extreme events and then, follow a training and testing and split the strategy in a way that you can account for those extremes in the training set. But with LSTM, you need to at least have several years of time series data to really connect the long-term patterns with the predictions that you want to have. So what we see here is that if you use a bidirectional LSTM without the attention layer, in this case, so the red dots are annual maxima values, the performance is not good and cannot even capture what is the peak. So that's why the attention layer is gaining popularity in the machine learning community, because it's helping account for those patterns and using model weights that can inform the machine learning model where to put emphasis on the patterns and therefore capture the extreme water levels, as you can see with the green color. And what is the criteria? So because we are interested in the evolution of extreme water levels, so we decided to use the Klein-Gupta efficiency in terms of magnitude and the Nash-Sutcliffe efficiency, NSE, in terms of timing. So for those, remember that we have multiple hyperparameters that lead to a machine learning model, to LSTM model. So the LSTM models where the KGE and NSE is greater than 0.7 are selected to be transferred or to be transferable to other stations. And after following that criteria, we got very interesting results. So let me start with the middle panel, the station number 4, for example. You see that the transferable models, so in this case 18 that meet that criteria, are able to capture the evolution, the onset, the peak, and dissipation of extreme water levels. The top panel shows that in some stations that for whatever the reason, you don't have information, actual observation. So in this case, for Hurricane Sandy, the station Sandy Hook, the gauge failed. So it was not providing information, complete time series data. So the LSTM model was able to capture the extreme water level variability, as you can see here. And that's similar to process-based models. So if in some station you don't have information, the process-based model can complete the time series data. So in this case, LSTM is also completing the time series data, and you can see the potential of using LSTM. However, there are some challenges, and that's related with the physical conditions. And that's why we really need to transfer models having similar site-specific conditions. So in this case, we transfer the models to this station, for example, Oregon Inlet Marine in North Carolina, and we noticed that the performance was not good in terms of those water levels. So the peak was almost captured, the timing was not that good, but the very low water levels, the onset and the dissipation was not very well captured by the model. And the reason is that those tide stations are protected, so behind barrier islands. And that's one of the limitations. So how to account for those site-specific conditions in the model, how to constrain the machine learning predictions. That's something that right now we are working on, especially in the Gulf of Mexico, because most of the tie gauge stations that we have down there are behind those barriers. So there are some input features that should be removed from the training process in order to achieve a similar performance as those that you are seeing in those upper panels. And the last one, the last application, we are finding time, I guess, is accounting for uncertainty. So we can use process-based and machine learning models to characterize cascading uncertainty in compound flood modeling. And so I'm bringing back the different sources of uncertainty, initial condition, forcing data, model parameters, and structure. And what I did is basically play with those scenarios and calculate the water level residual. And that is basically the input features for a machine learning model. So in other words, let's take, for example, a scenario number 2. So the operational surge models like AdCirc and SERA, they provide storm surge predictions ignoring the effects of rainfall and river discharge. So they assume that rainfall and river flow do not affect those coastal areas. So if you have a benchmark model scenario, so in this case, Delft3D, because it outperformed HEC-RAS, you can calculate the spatiotemporal variation of residuals. So the difference between the water level that you have with the benchmark model and the water level from a scenario 2 that ignores rainfall and river discharge. The same with all those scenarios. So scenario number 3, in this case, if you use a model that was calibrated for a event, let's say, in this case, I'm showing you Galveston Bay. So a model that was calibrated by Hurricane Ike in 2008, if I'm not wrong, and then use those model parameters to simulate Hurricane Harvey, for example, in 2017. So what is the uncertainty behind that? So this leads to different residuals. Once again, the red color represents an overestimation of water level, and blue color represents an underestimation. Obviously, if you ignore rainfall and river discharge, the water level, you underestimate the actual water levels, especially in those coastal areas. So this is Houston. So multiple linear regression model can be used as a benchmark model to aid in explainable machine learning. And that's the goal, because if that's the advice that I have for my students, if you are going to develop a machine learning model, first show me that you understand the process, or you have a benchmark to compare with your results. So in this case, a multiple linear regression model was the baseline to analyze what's going on with this nonlinear model that we want to capture the different interactions of sources of uncertainty with respect to total uncertainty. So the input features, the water level residuals of those 4 scenarios. We have a regression model, linear and nonlinear, and then the target variable is total or combined uncertainty, which is basically a scenario that contains all the different sources of uncertainty. So scenario number 1 is uncertainty in input data. So if you do not correct for wetland elevation, for example, scenario number 2, you ignore river flow and rainfall. Scenario number 3, you calibrate your model with parameters of another tropical cyclone event, and you use a model, for example, HEC-RAS, that do not account for different physical processes, for example, wind and atmospheric pressure. So that's the total uncertainty. And then to compare those 2 different approaches to account for uncertainty, we compare the variable weights from the multiple linear regression and different methods like feature importance and permutation importance. So those are the results of the benchmark model. So this equation represents, is a function of total uncertainty and the different sources of uncertainty, S1, S2, S3, and S4. So as you can see, the performance of this multiple linear regression model is not that bad. So it is rather good, right? And then from that, if you analyze the correlation between the different sources of uncertainty with respect to total uncertainty, we have different plots and colors, and you see that the correlation, the Pearson's correlation is high for input data and forcing data. So forcing data has a higher correlation than input data, and then model parameters and model structure have a negative correlation but still those correlations are statistically significant. Now you see forcing data first and then input data. Now pay attention to this figure. When we use a nonlinear regression model, so in this case, random forest, we got better results. So we can capture those interactions among the different sources of uncertainty and then predict what will be the uncertainty for different scenarios. And having the benchmark model is an explainable machine learning model. So when analyzing the feature importance, we saw an agreement between the random forest and the regression model. So the first source of uncertainty that contributes more to total uncertainty is forcing data, followed by input data, and you see that model parameters and model structure are about the same, so which is consistent with the results that we got from the multiple linear regression model. But that was just the different contribution of the sources of uncertainty to maximum water level. But uncertainty changes over time. And also the source of uncertainty, the importances change over time, as you can see here. So what we did is considering all the different grid nodes of this model domain, and I'm using here a tie gauge station water levels from a representative station located in the middle of Galveston Bay. When analyzing the importance of those different sources of uncertainty, at the beginning of this extreme event, model structure is the most important parameter or source of uncertainty. And then as soon as you see the peak of water level, model structure drops, and then forcing data becomes the major source of uncertainty. And when we calculated the cumulative importance as well, and if you analyze this event from onset, peak, and dissipation, then model structure is the most important source of uncertainty that you should take into account, followed by forcing data, model input, and model parameters. And the benefits of using machine learning models. So the solid lines represent different evaluation metrics from the multiple linear regression model, whereas the dashed lines represent the same scores using a random forest. So you see that if you use a machine learning model, the performance in terms of predicting uncertainty is higher and is not subject to those changes, changes in extreme water levels. As you can see, those peaks, this drop in performance of the multiple linear regression model, and even the root mean square error is lower when you use a random forest model. So with that, the take-home messages of this talk, the first one, component flood modeling requires a complementary process-based and statistical understanding. So it is okay to develop process-based models and characterize hurricane events, but if we want to develop flood hazard scenarios, we must account for statistic dependencies, as you saw in this chart, that most of the gauge stations and locations in the coastal US have flow drivers that are statistically dependent. State-of-the-art hybrid approaches, for example, machine learning, can help us unravel nonlinear and hidden associations. As you saw with cascading uncertainty, those nonlinear interactions among the different sources of uncertainty are better characterized using a nonlinear regression model or machine learning, in contrast to multiple linear regression model. Transfer learning is suitable for compound flood mapping and extreme water level prediction. So I showed you two examples of conducting transfer learning for compound flood mapping in the southeast coast of the United States, and also using LSTM and transfer those models to estimate extreme water level prediction. The sources of uncertainty can synergize in cascade, and obviously that affects compound flood modeling. So we need to account for also nonlinear interactions between or among the different sources of uncertainty. Regarding the limitations, the need for spatiotemporal data is still a major challenge in terms of training and validating models, regardless of process-based models or machine learning models. We are having more information, spatiotemporal data, for example, the SWAT mission that is going to provide more information And the combination in data fusion of remote sensing information with in situ observations and even process-based models can help characterize those component flow hazards with a higher accuracy. And future work, something that my students are working on right now is ensuring model transferability across the scales. So for example, models that are trained in the Gulf of Mexico, is it possible to transfer them to the Atlantic coast, for example? Can we have models developed in the US that can be transferred to Europe? So that's something that we are studying right now, and also the underlying physics. So what are the conditions? What is the criteria to really transfer models across the scales and even across continents? And that's it. Thank you very much for your attention.
Thank you so much, David. Definitely sparked some questions for me, but I'm gonna hand it in the few minutes we have to the audience. Feel free to raise your hand, jump right in, or drop something in the chat if you'd like. I'll give you a second. I know we have a range of folks on the seminar today, from engineering to oceanography to applications. But actually, I'll go ahead and jump in with one. I liked your work on LiDAR and elevation modeling. I'm wondering, do you see that as still a persistent data limitation? The marshes, the hydrocorrection, as you go into estuarine areas with an abundance of marshes, like you showed with Savannah Delta, is that something that you think could also be open to, learning or more extensive correction across the elevation models that we use to build flood models?
Well, that's an important source of uncertainty, especially in terms of coastal flood hazards in those ecosystems. I know that right now people are working with machine learning models to combine the RTK information that are collected, and then using that information to improve the DMs that we have from NOAA. There is even a product, the author, I'm trying to remember his name, Almquist, I guess. So he published, or she published, I'm not sure, a wetland map or DM correction for the entire continental United States. And that's actually the source of information that I use to compare what are the errors with the LiDAR DMs that we have from NOAA, for example. So I'm not an expert on data collection, but I know that people are working in trying to use machine learning to improve the vertical accuracy of those maps, especially within wetland areas.
Yeah, you gave some good examples, caveats and cautionary aspects. I wonder, Naveed, were you going to have a question? Go ahead.
Yeah, I was looking for the raise hand feature.
It's always moving around.
Anyway, I can do it here. So you shared some results of the work on where your model did not produce water level that you were happy with for a sheltered area. I was not sure if that was a surrogate model or was pure machine learning model trained with water level gauges. So which was it? Is it you had
it was a
base
LSTM
model? Was a surrogate model?
Yes, it was a machine learning.
Oh, it was a pure machine learning model.
Mm-hmm.
Okay, so that makes sense because we had a similar we had a paper came out earlier this year actually. So we tried to connect using a deep learning model LSTM with to connect wind field to surge observation. And there was a very strong correlation, but there were areas that we had issues, like north of Chesapeake Bay, we had issues. Mm-hmm. With open areas, we had no issues, like Swells Point, Chesapeake, CBBT, the south side of Chesapeake Bay, even mid areas, correlation was really good. So I was wondering if there was like issues with rainfall and runoff that could have caused those discrepancies you saw, not necessarily maybe shelteredness of the area. So I was wondering if you had that in the model or no, because again, that's an important input potentially. But then if you had, then maybe connecting, looking into wind field impact could bring some additional, could bring input to the model. Although shelteredness will still be an issue in that situation, even if you have wind input. So I was wondering what your thoughts are about that discrepancy. And the question I have there is, do you have rainfall or river discharge there or not?
Yeah, so that's a great question, and input features obviously are important to really predict water levels or coastal water levels. So the study that Sam conducted was just along the coastline. So we didn't really go further inland because we know that there are some forcing conditions that are important and should be taken into account. For example, you mentioned rainfall, for example. River flow is another input feature that should be considered to really capture the extreme water level variability. What I can tell you is that when we did the transfer learning in the Gulf of Mexico, because there are many stations that are behind barriers, what we notice is that the wind, the wave component is not that as important as in areas that are, open to the ocean. So when we remove the wave component as an input feature for areas, then the performance of the model increased, especially behind those barrier islands. As I said, those 3 stations that I show in the Atlantic coast are just examples of, understanding the physical process. But I think that to really identify what are the ways to improve the accuracy is playing with the input features. There are tools to analyze the importance more advanced. So for example, the SHAP tool that can give you, better understanding of in terms of which input features are really contributing to the model performance. So summarizing again, by removing wave input, we realized that the models were performing even better than the models with it, just because those are protected against wave impacts.
Yeah, interesting. Although wind, just a quick note, wave and wind stress impact on water level, they are very much related. So in a sheltered environment, you don't expect much surge either because it's sheltered. So,
Yes,
and you don't expect much waves.
we accounted for wind as well as part of the input features for coastal water level. Pressure, and even temperature, and we realized that some input features are not really correlated with that. But as I said, if you move inland, then obviously there are some hydrological processes that need to be taken into account.
But you had wind in this one, or didn't you?
Yes, I did.
And you didn't find a strong correlation there.
No, wind was an important
Wind was
factor
important. Yeah.
in the coastal areas, right?
Yeah, that's what I would expect.
Because waves, we realized that by removing waves in the training process, the performance was better.
Okay, interesting.
Good discussion.
Yeah,
we're right at time. I see Jim came on. Do you have a burning question?
Yeah, it's locally. I work for a natural event mitigation advisory committee in the city of Chesapeake. But one of the things we're running up against is the local planning commission is playing with increasing the sensors, the border level sensors, both in the tidal areas and non-tidal areas of the Hampton Roads area. But they're balking at the cost and the maintenance. But it appears from what you're saying that really we need to fill in the gaps for our predictability in this area. And so it sounds like I just want to sort of verify that more sensors are better. I mean, you can do too many. I mean, you run out of money at some point. But it seems like I need to recommend back to the Planning District Commission that they really look at putting the sensors in place and paying the freight for the maintenance and the and collecting the data.
Yeah, the more data, the better. That's true. I mean, if you have more information, then you can improve the model performance, and you can even conduct more advanced analysis. So for example, if you have real-time data, something that is working very well, and I know from some colleagues in Georgia that are using data simulation in real time, and they are like improving the performance of prediction, even with process-based models. So the advantage of, once again, those machine learning models is that they can fill the gaps. You know, if there are specific conditions that are similar, then can be used to predict, okay, the extreme water level variability as we did in this study.
Good point, Jim, and thanks for the question.